welcome back, everybody. So we are going to continue going through this introduction. Today is a bit special, right? It's not, I'm not yet throwing math at you, but we will have some math during the semester. Today is really just an appetizer and a high level view of our things. So I left you with this cliffhanger that is almost worth a Netflix series, season final. So this is the problem we have. We are in big trouble because now we produce so much information and we can actually barely read it fast enough. And in fact, Vannevar Bush, I told you earlier that he was actually a visionary. That's exactly what he was saying back then. Publication has been extended far beyond our present ability to make real use of the records. This was in 1945. Transistors did not even exist back then. So just to illustrate how big the big trouble that we are in is, almost using the German order of words now. So capacity, an example, if 600,000 of words, that's a book. That would be the capacity of a book by analogy with a hard drive. Now, what would be the analogy of the throughput is that you can read maybe 1,000 words every minute as an order of magnitude. And the analogy for the latency, in the sense that I'm using it, would be 1 minute, because you need to get up, go to the shelf, take the book, open it at the right page. So that would be the latency of 1 minute, right? But I'm more interested into capacity and throughput for what I'm going to show you now, and latency a bit less. So what does it mean that we have this capacity and this throughput? Well, with a simple division, we can derive how much time is going to take me to read the book, and that's 10 hours. That sounds reasonable, right? Maybe if it's the latest Dan Brown, it's going to take you less than 10 hours, but this is roughly the time that it could take possibly to finish a book. Now, if I now let things evolve with exactly the same factors that I've shown you that actually happened between 1956 and 2024, that actually happened, and now I increase the capacity of a book by the same factor, I have so many zeros that I cannot even read them, the number of words that there would be in a book. But 21 million, that's less zeros, words per minute. Now, if you do the calculation, the time that it would take you as a typical human being in 2224 to read a typical book of 2224 would be 1,100 years. That is the trouble that we are in. Right? The fact that we produce so much information that just reading it has become unmanageable. So that's the problem we have. But we have a solution. That's the solution we found in big data. We use exactly that same trick for information retrieval when we want to index collections of books that are extremely large. We parallelize. So that means that if you could spread all of the effort of reading across 200 million people, there are more than enough on the planet, you could actually still read it below 10 hours, right? So if you parallelize everything. And that, in fact, would be what leads us to data centers with plenty of machines. And everything you imagine, like when you train models like OpenAI, ChatGPT, and so on, this is how it's done. It's done in parallel with enormous quantities of machines. And we also have a solution for throughput versus latency. And the trick, you're computer scientists, so I think I can just explain it to you that way. Imagine that you connect via SSH to some remote server, and you want to upload 1 million files. It's going to be slow, right? Why is it going to be slow? Because every file you have latency, right? Every file you send, you're going to have latency. Imagine these are very small files, like 1 kilobyte per file, but you have 1 million of them. So it's going to be slow because latency per file. How do you solve that? How do you upload 1 million files that are small to a server more efficiently? Anybody? Yes? Yes, that's exactly the idea. You concatenate it to one file, which you could also do with a jar, right? So you put it in a zip or a jar file or a tar file, and then you upload a single file that is basically containing all the files. So concatenated exactly is the idea. Why do you do this? Because then you have latency only once. When you transfer the file, then it's just throughput. You just send the bytes over the network. right? For whom does that make sense, that sending a single tar file is going to be much faster than a million small files, right? Who already did that to ship data to a server? Some of you, right? So that's the experience. So that's called batch processing. The idea of doing that. You avoid the latency by grouping into batches the way that, that things are processed. All right. So now, if I look at this, I told you data, information, knowledge, and wisdom is the fourth one. This is basically the whole stack of the data stack, if you want. There's a lot of things happening in there. Some of them have become buzzwords that everybody in the world knows, but we are not going to cover them. I'm going to focus on the database. I call it database, right? But just the non-machine learning aspect of information retrieval. If you look at the textbook that we are going to use, half of it is machine learning. There is a link between machine learning and information retrieval, right? Who is following the introduction to machine learning lecture this semester at the same time? Right, so this is complementary. In fact, a lot of things that you learn there are directly applicable to information retrieval. But of course, we have to make sure that we don't overlap too much between the courses. So this is why I leave the machine learning parts to Professor Krause, and I will focus on the complementary part for information retrieval. But I might make sometimes bridges with machine learning. All right, so we focus on that. We have a TA team of which I didn't receive all pictures, but this is the team who is going to support you during the entire semester. That there will be the exercise sessions, support during the week. So we have Marco right here, who is moderating the lecture every week, which is an opportunity to say that you can ask questions. You can raise your hands directly in the lecture hall. You can also on Zoom write your questions to the chat at any time, and Marco will then interrupt me so that I can answer, right? So it doesn't matter if you're in the lecture hall or on Zoom, it's the same. All right, so we have Zichen, Panos, Denit, Piriakor, Namir, and Marco, who are the wonderful TAs who will accompany you throughout the semester. Even though they cannot hear us, let's applaud them. Maybe they can hear us if you do it loud enough. For Marco. All right, so now here's the menu of what we are going to do during the semester, and then a bit more about what the course unit is made of. Today was the introduction. Next week, I'm going to teach you the basics of information retrieval, starting with Boolean queries. It's the easiest way you can query some text. So it will involve, you have an eBNF grammar. Who knows what an eBNF grammar is? Context-free grammars and so on, right? You know that, right? So this part, of course, we won't cover, but you basically have a language with a grammar and so on. We will give it to you pre-parsed in a Jupyter notebook. And then you can come up with a Boolean language with which you can already look up words in some text. So this is what we'll spend a week on. It's a smooth start, a bit of math, but not too much. Then we'll look into term vocabulary and posting list, because in the first week, we'll make a lot of simplifying assumptions. And then in the week after that, we'll realize that these assumptions are oversimplified and reality is actually more complex than this. So in this week, I will explain to you how the fact that we have a diversity of languages in the world makes it very challenging to build systems, because a lot of things depend on the language and on the grammar that you use. We will also look at tolerant retrieval in the sense of spell checks. You already notice if you make a mistake in a search engine, it already suggests corrections. Sometimes it might even correct it without asking. So how is this done? This is what we are going to cover in tolerant retrieval, right? At that point, we will have covered the basics, right? This is the fundamentals of information retrieval. And after that, you will be able, if you want, to take a collection of text. There are enough you can download from the internet. There's a lot of things that have become public domain now. You can build an index on it. You can build an engine that accepts a query and efficiently returns the results, possibly even fixing mistakes and taking into account some language particularities. So at that point, you will be able to do this. In fact, we will have programming assignments, so you will even write code in order to do some of this, to provide you with a bit of experience. So now that we've done that, we'll switch over to a slightly more advanced part, and we'll start scaling up. What that means is that the first exercises that we'll give you, the document will fit on a computer. It will be small enough that it's simple. You don't have to worry too much about performance. But the thing is, in real life, if you want to index the whole internet, it's not as simple as downloading as a small file on your laptop and processing it without worrying about performance, right? Then you have to worry about performance. This is where these aspects of big data with the batch processing and parallelism will start mattering. And we'll have a week where we look at that. How do we scale up? How do we manage to build the same thing we've built in the basics part, but much bigger, for much bigger amounts of data, even when it doesn't even fit on your laptop, because there are ways to do that. Then we look into index construction. Here, the idea is, and that I will repeat it many times, before you buy more computers, you should try to squeeze more on the computers you have. It costs much less. And if some of you create startups, that is one of the most valuable advice that you can have for a startup. Try to squeeze as much as possible on the machines you have, and very often on a single machine. You don't even need to parallelize in many cases. So this is what we'll be doing with compressing the data. So constructing and compressing the data to squeeze more information into less bytes to save on costs. And it's beautifully mathematical in this week, but it's truly amazing what people have invented in order to compress the index. The index, by the way, that we construct and process is the same one that we'll cover in the basics, right? So this is really just taking things to the next level. And then we'll turn to something completely different from the Boolean indexing. It's a different approach. That's called the vector space model. And here we are going to use linear algebra. Who loves linear algebra? Who loved the lectures? Right? It's beautiful, right? We're going to apply it. You already know it applies to machine learning, right? But we can also apply it to information retrieval in this way. And just in vector spaces, we will be able to query data in this way. So I love that part. There is kind of I would say, a link to these large language models. You might have heard of word embeddings and so on. This is not quite it. It's not a word embedding in the sense that we would have the words here, it's the documents. But still, it kind of starts bringing you in that direction when you start abstracting things away in linear algebra. Okay, then we'll optimize, because what happens when you start using this linear algebra is that it gives you a feature that you didn't have before, even though it's obvious now, because whenever you type words in a search engine, you get the top 10, right? It's sorted. You have an actual scoring that happens, and it returns the best 10 results first. So how is this all done? How can we optimize scoring in such a way that out of the entire internet, these are the 10 best web pages corresponding to your search? How can we actually do this and optimize things a little bit? Then we'll also look at evaluation. Here, there will be a bit of a bridge with machine learning, because some of the things we'll see in there will probably be similar to what you use to evaluate machine learning algorithms too. So how do we evaluate information retrieval systems? How do we estimate the quality of what you have just built? So we look at a few metrics that we can use in there. At that point, once we have covered the basics and the advanced topics, we will basically have covered everything that is typically taught as the bachelor's level in universities for information retrieval, right? So this is you get your bachelor's degree. But I want to push you a little bit. So we are going to also do master's level things, which shouldn't scare you, because in fact you are allowed to take master's lectures in your third years of bachelor's. So I'm going to show you alternate methodologies. The first one involving probabilistic information retrieval, which is yet another way of querying the data. It will involve random variables, omega spaces, the Bayes rule, and so on and so on. So that's going to be math heavy, but you don't have to worry. We'll take the time to go through it in that lecture. And I'm not saying much, but at the end, there will be a nice surprise at the end of that, a mathematical surprise, I mean, intellectually satisfying surprise, probabilistic information retrieval. Then, now that's probably where the focus is nowadays, but we'll look at language models. It's not going to be large language models in the sense of ChatGPT, but some of the aspects go into that direction. There is already a lecture for large language models at ETH. But what you will see in there is that the concept of generating words after words with probabilities is actually not new. It's several decades old already. That's called the language model. And we'll look into these and all the various ways that you can instantiate them. Plus, at the end, we will infer from that yet another way of building an information retrieval system, of looking up some information in documents. There will also be a surprise at the end of that lecture, in the sense of intellectually satisfying surprise at the end of the language models. That kind of unifies and connects everything together. And if time permits, I might say a few words on PageRank and how you can actually sort the pages over the web. That's the algorithm that Google was initially based on. Now it's probably evolved a little bit. All right, so that's the overview of the lecture, everything that we are going to cover during this semester. So I hope that I can transmit the passion for all of that. So what is expected is that you have the weekly lecture every Friday from 10 to 12, just like right here. You can be in the lecture hall like this. I mean, almost everybody now is in the lecture hall. A few of you are on Zoom, but it's your choice. If you want to attend on Zoom once, you can also connect to Zoom. Some prefer to watch the recordings, which is fine too, but with the recordings, you don't have the interaction. There's two benefits of attending live. First is the interaction. You can ask questions live. The second benefit is that if you learn during the semester and you do the exercises during the semester, it makes it much easier for your brain to process and remember. It's magic. This is no effort at all besides doing it every week, and that's already 80% of the way to memorizing things. You can see it, in fact, who uses Duolingo, for example, to learn languages? Some of you. Have you noticed how doing it every day for a few minutes, you retain the information much more than 1 hour every 2 weeks, for example? So the amount of time, if you distribute it, that actually your brain memorizes it more, and then you're less stressed for the exam. So this is why I still recommend that either here on Zoom you attend. Then we'll have the exercise session, which is on Fridays between 4 and 5. So you have the groups. You can register in My Studies. They are already available. One of the groups is going to be a hybrid, Amir's group. So if you want the option to connect via Zoom, you can also register to that group. I think that many of them are on the 8th floor over there, and some in the CHN building, and one session in the HG building on the other side of the street, right? So just make sure to register to your session. And then you have a textbook, the Introduction to Information Retrieval textbook. It's a really good textbook. You will find it in the library. In fact, it's also online. So you also on the Stanford webpage, you can see the PDFs. So it's important that you read the book, because that's, I'm going to tell you more or less the same thing, right? But you have two angles. So it's also good for you to consolidate the knowledge in this way. Then every week you're going to have theoretical exercises, and you are also going to have programming exercises. It's curated in the sense that there was a lot of efforts by the TA team to give you the focus every week on one specific programming assignment, not 2 or 3, just one. There is a focus every week. And then there is this programming assignment that you need to solve, right? So I highly recommend that you do it, because when you program things, then you know you truly understand what is going on. It forces you to understand the details. So you have a good mix between theoretical and practical. And then we have the written exam in the summer session. So this is between the 5th of August and the 30th of August. Unfortunately, I cannot give you any date because first, I'm not the one deciding, it's the exams office. And I think they announce it in May or something, probably the exact date of the exam. It should be 180 minutes. What is legally binding is not my slide, it is in the course catalog. So if you go to vvz.ethg.ch, but I think I checked, it's 180 minutes. So 3 hours. I'm trying to be generous with the time. So 3 hours doesn't mean that you're going to be inundated with questions. The goal is more to give you enough space and time to process the questions. But we try to target an exam that can be solved in 2 hours, roughly, and you just have a bit of time buffer. The exam is going to be computer-based. It's going to be a Moodle interface with questions, and you just answer the questions on the computer, right? Sometimes it's in Oerlikon, in the ONA building. Sometimes it's in the main building, and there is also a new building in the Gloriastrasse that we had it for the first time last semester. So there are a few places where this is. Has anybody done a computer exam already? Yes, many of you. Okay, so you will be familiar with this. And the Moodle is going to be similar to the Moodle we'll use during the semester as well. And if you pass the exam, you get 4 credit points, plus bonus points. You can, if you work regularly during the semester, earn a quarter point that gets added to your exam grade. How to do this? In 3 weeks during the semester, and we will tell you which ones, you will have a graded Moodle quiz. Possibly you need to program something to solve it, but you will have questions. If you pass 2 of these 3 weeks, then you get the extra 25, right? It's all or nothing. So if you don't pass one of the first 2, you still have the third one as another chance to get the extra bonus, right? Just as a disclaimer, if you already have 6, you're not going to have 625, but I think this is obvious, all right? So I encourage you, the bonus points, it was introduced and I think put in the regulations a few years ago as continuous performance assessments, ETH-wide. It's basically a guideline for organizing this. And the experience that we've learned from doing this is that it doesn't seem like a lot, the 0.25, but it really works on the motivation, on your motivation in our experience. So in almost all of my classes, a lot of the students, a majority of the students got the bonus points, right? So it's within your reach. And what's amazing about the bonus points is that this gives you a motivation to learn during the semester, which is exactly the goal. So the real benefit of the bonus points is more than the 25. It's the 25 plus the higher grade you're going to get if you actually work during the semester, right? So it's a leveraged bonus points if you want to see it that way. Okay. This is a very good book that we are using throughout the semester by Professor Manning, Professor Agravan, and Professor Schütze. It's in the library, so you can find it. You can also find it online, and almost every week there will be a chapter of the book that corresponds to what I'm going to tell you, right? I think there's just an offset of 1, like in week 2, it's chapter 1, in week 3, it's chapter 2, and so on. At the end of the semester, it's no longer going to be linear, right? So I might jump chapters or not exactly in the right order, so pay attention. But in the first weeks, it's relatively linear in the book. So the programming assignments will be in Jupyter Notebooks with Python. Who already knows Python? Many of you, right? Okay, very good. So this is what we are going to use. If you don't know Python, who doesn't know Python? Some of you. You can learn it, right? So as a computer scientist, you can basically learn any language very easily because in the end, they are really all the same concepts, right? Okay, so we have Python. So the question I wanted to ask was what I asked, and you raise your hands. So most of you know Python. This page here is the Moodle of the course. This is where you are going to find the slides of the lecture, the pointers to the chapters of the book, the pointers to the YouTube recordings, the links to the exercises. You can download the exercise PDFs. You can download the notebooks and so on. So everything is going. Maybe not the notebooks. I will explain with the server. But this is the place where all the information is. We also have the announcements are sent through this. I think the announcements are also automatically sent by email. So it's a forced subscription. What is also in the Moodle is a forum. So Moodle Overflow, it's the equivalent of Piazza, but locally hosted at ETH. And you can ask all the questions you want in there. Have we decided in the TA team if it's the Moodle forum or the chats that you prefer? Not yet. We will tell you. One of the two guarantees you an answer. You can use both, but for one of them, the TAs guarantee an answer. We'll tell you which one. What else is there in the Moodle? Yes, in the Moodle, there's also the past exams. I don't know if we made them public yet, but at some point, maybe towards the end of the semester, we'll give you all the past exams that you can work on. If you're really impatient, then you can go to the FIS examination archive. They already have them. There's even community solutions that are quite useful to prepare for the exam. All right, so that's the Moodle. Then we have changes every year. We have a service hosted by the department, which is a Jupyter Notebook service that we will use for the course. And every week you will find the Jupyter Notebook with a programming assignment on that server. I don't think it's configured yet. This is being set up right now, so I cannot guarantee that if you connect now, it's going to work. But normally next Friday will be when we will start asking you to try it out, right? So this is the address, students-jupyter.int.ethz.ch. It's used by, who uses it in other courses? Not so many, because this is really a departmental service. So this is, you get every time, I think, 4 hours of CPU time every week in order to solve the assignments. If it's not enough, I hope we can negotiate with the ISG to get a bit more CPU time. Okay. By the way, the picture is unrelated. We are not going to do any such things in this lecture, even though I would actually love to, because it looks very exciting, but this is unrelated. Then we have a chat server element. You should connect to this website right here, chat.ethz.ch. You might, for some of you, already be connected there. I've already invited you, at least all of you who have a student.eth.ch email address, I already invited. A few of you have an in for another address. I will also invite you, but it needs to be converted to the handle. So I'll do it as soon as it's done. So you can go there. If you're a student, you need to pay attention. There's the staff on the left and students on the right. You need to go on the right of the screen, and you have to connect with your existing ETH credentials. It's not about creating a new account. It's your existing ETH credentials that allow you to connect there. And then you should see normally the course in there. Does anybody see it? Like if you connect right now, does anybody see the chat room of the course? Yes, you see it? Awesome, perfect. So most of you should find it. So it's a great place to interact with each other. If you want to discuss the material of the course in the main room, you can also ask us questions. We'll be here as well. So it's a great way of basically networking and connecting amongst each other during the course. Okay. The exercise session starts next week. Today there is no exercise session, so please do not come at 4 p.m. to the room because there will be nobody. We start next week. And next week will be about making sure that the Jupyter notebooks work nicely for all of you. This is what we'll focus on. And then we'll offset the exercise material by 1 week every time. So we do Boolean retrieval next week, and the week after that, the exercise is on Boolean retrieval. That's for spaced repetition. So that way your brain every week gets the opportunity to revise and repeat the content. That's also better for the retention of knowledge. There are 5 in-present sessions. I don't know why I didn't update that. So 5 sessions. And one of them, that of Amir, is allowing a hybrid participation. Is that the last slide? Yeah, I think it is the last slide. So you've just earned the right to go for lunch a bit earlier and avoid the queue. Do we have any questions? Anybody? No questions? Who understood what happened today? Okay, great, most of you. So again, today was special. It's just an introduction, just an appetizer. And next week, we'll dive into Boolean retrieval, and then we'll start doing covering actual material. Thank you very much, everybody, for attending. I hope I motivated you to continue attending the lecture. I'll see you next week at 10 a.m., same room, or on Zoom for the continuation. Thank you very much, everybody.